Everyone, my name is Joshua Ferguson. Today I'm going to be presenting the paper Attention is All You Need, which introduced the transformer architecture that is very prevalent today. It was published in 2017 by Google Labs, and it introduced the transformer architecture or model, which does sequence-to-sequence tasks without relying on recurrence or convolutions, instead relies on attention mechanisms. The key challenges or problems addressed in the paper was mostly just sequence transduction problems, which you could kind of think about as translation problems, as if you want to go from one language to the other. It's a many to many, and transformers improved on this kind of translation tasks and general sequence transduction without the reliance on recurrence or convolutional operations, which was the standard before Attention is All You Need was published. It also improved upon the context awareness and long-term dependencies. So with sequences who are very large and where relations between words in one place relative to another, when that distance is large, recurrent neural networks would be prone to the vanishing gradient problem. Transformers use self-attention to weigh all the other tokens of the sequence regardless of the distance, which ensures this contextual awareness. It also allowed for parallel processing. So as recurrent neural networks would have to depend on the I-1 input in order for it to derive its output, the transformer architecture and the attention mechanism allows processing of each positional input on its own in parallel, which significantly enhances the training efficiency and scalability over long term. The main papers that Attention is All You Need was based off of was the 2014 paper introducing the attention mechanism by Bottineau, and this just worked to get this context awareness of different positional inputs to work well and avoid the vanishing gradient problem. His implementation was with recurrent neural networks. Transformers applies this attention mechanism without the traditional architecture of a recurrent neural network. So going into the technical details, the transformer model still follows an encoder and decoder architecture. The encoder input is going to be an input bedding, which is a vector representation of the text or words. We can kind of just think about it as we get a vector representation of the word, we can do math on it and do different operations on it, which is the core of what this is going to be doing. So the encoder kind of structure is going to be made of identical layers, n equals 6 in the paper, and this is going to have two sublayers, a multi-head self-attention layer, and then feeding into a normalization, and then a position-wise fully connected network. There are residual connections between before the multi-head attention to the norm, and then before the feed forward to the norm. The decoder is very similar structured to the encoder, except it features its multi-head attention is its input is from the output of the encoder stack after all the layers have been after all the sublayers have been processed in the encoder. So the main attention mechanism is going to be called the scaled dot product attention, and this is taking a query Q and then a set of key value pairs K and V to an output. This is the result of multiplying the input embeddings, which is the vector representation of the words, to coordinating trainable matrices WQ, WV, and WK. And we can see the mechanism and exact calculation for that over here in the diagram in the slides. And then this is all going to be fed into a softmax function to get a probability distribution. The multi-head attention is what's actually in the sublayers, and this is just a number or H number of parallel scaled dot product attention functions. And this is supposed to aggregate information from varying representations at different positions. You can see the exact technical details over here, which is just meant to, we can cat the different heads or parallel operations, and then each head is the trainable matrix times the Q, K, and V values. And then that's going to be concatenated and fed into the linear layer out of the decoder. After the transform or decoder spits out its output, it's going to be the model's predictions for each position in the sequence. So what's most likely to come after that. And it does that through a linear network and then a softmax function. Its results did very well in terms of translation tasks. In the paper, it performed better on blue than any other model or architecture at the time, and has since become the standard for these kinds of sequence transduction tasks. So, in conclusion, the transformer, the architecture proposed in attention all is all you need, replaces recurrence with multi-head self-attentions to work on sequence transduction tasks. And attention is approximating the degrees of importance to different words in a sentence without the vanishing gradient problem. In the paper, the future work mentioned was to look at different kinds of input data instead of just text, but things as image, audio, and video, which video can be sequential data in terms of sequential images.